Hi, this is the last video of the section, Estimating Bicycle Demand Distribution. In the previous video we looked at computing the relative importance of the features. In this video we'll solve the bicycle demand distribution problem. Here we'll use the random forest regressor to estimate the output values. A random forest is a collection of decision trees. This basically uses a set of decision trees that are built using various subsets of the dataset, and then it uses averaging to improve the overall performance. We'll use the bike_day.csv file that's provided to you. This is also available at this link. There are 16 columns in this dataset. The first two columns correspond to the serial number and the actual date, so we won't use them for our analysis. The last three columns correspond to different types of outputs. The last column is just the sum of the values in the 14th and 15th columns, so we can leave those two out when we build our model. Let's go ahead and see how to do this in Python. You've been provided with a file called bike_sharing.py that contains the full code. We'll discuss the important parts of this. We first need to import a couple of new packages. These are the packages. We are processing a CSV file, so the CSV package is useful in handling these files. As it's a new dataset, we'll have to define our own dataset loading function. In this function, we just read all the data from the CSV file. The feature names are useful when we display on a graph. We separate the data from the output values and return them. Then we read the data and shuffle it to make it more independent of the order in which the data is arranged in the file. As we did earlier, we need to separate the data into training and testing. This time, let's use 90% of the data for training and the remaining 10% for testing. Now let's go ahead and train the regressor. Here, n_estimators refers to the number of estimators, which is the number of decision trees that we want to use in our random forest. The max_depth parameter refers to the maximum depth of each tree, and the min_samples_split parameter refers to the number of data samples that are needed to split a node in the tree. Finally, we evaluate performance of the random forest regressor. As we already have the function to plot the importances feature, we'll just call it directly. So let's run the code. So we get this graph. We can see the temperature is the most important factor controlling the bicycle rentals. Let's see what happens when you include 14th and 15th columns in the dataset. In the feature importance graph, every feature other than these two has to go to 0. The reason is that the output can be obtained by simply summing up the 14th and 15th columns. So the algorithm doesn't need any other features to compute the output. We just have to make the changes in the load_dataset function. We will save the file and run the code. As expected, it says only these two features are important. This makes sense intuitively because the final output is a simple summation of these two features. So there is a direct relationship between these two variables and the output value. Hence the regressor says that it doesn't need any other variable to predict the output. So this is an extremely useful tool to eliminate redundant variables in your dataset. There is another file called bike_hour.csv that contains data about how the bicycles are shared hourly. We need to consider columns 3 to 14. So let's make this change inside the load_dataset function. Let's run this. The feature importance graph will look like this. This shows that the hour of day is the most important feature, which makes sense intuitively if you think about it. The next important feature is temperature, which is consistent with our earlier analysis. Great! So that's all about bicycle demand distribution. Cool, isn't it? In this section we learned pre-processing data and label encoding. Then we looked at various regressors, and finally we used those concepts to solve real-world problems of estimating housing prices and bicycle demand distribution. Awesome! In the next section, we'll take a look at classifiers.